Hello, my name's Charlotte Dawson. I'm a consultant in adult inherited metabolic disorders at Queen Elizabeth Hospital, Birmingham, and also a consultant in chemical pathology. Welcome to this first introductory talk. In the lecture series we have planned for you in adult inherited metabolic disorders. In the course as a whole, you'll hear talks from colleagues from all over the UK and Ireland on the laboratory and clinical aspects of inherited metabolic disorders, with particular emphasis on their investigation and management in adults. We hope that this will not only help you in your exams, but also ultimately enthuse you to come and spend time in one of our IMD centres, and perhaps even inspire you to consider a consultant career in inherited metabolic disorders. So the course organisers, in no particular order other than alphabetical, are Dr. Duncan Cole in Cardiff, myself in Birmingham, Dr. Nish Guha in Oxford, and Dr. Chongyu Tan in Cambridge. So any queries you have about the course, please do get in touch with one of us. But our huge thanks go to all of our colleagues in the UK and Ireland for preparing and delivering the talks and contributing to their content in other ways, and also to the BIMDG for hosting the course on their website. So in this talk, we will be giving you an overview of inherited metabolic disorders, what they are, how they cause illness, a brief reminder of inheritance patterns, and then the final part of the talk will guide you through principles of treatment and principles of managing a metabolic emergency. So the study of inherited metabolic disorders all began with this gentleman, Sir Archibald Garrod, who was an English physician practicing at the turn of the last century. And he studied urine chemistry and how it caused human disease. And he was doing this at a fortuitous time where there was a growing understanding of Mendelian genetic inheritance, and coupling this growing understanding of Mendelian inheritance with his studies on urine chemistry led to his discovery of alkaptonuria. So alkaptonuria was the first inherited metabolic disorder described in which a genetic defect was linked to a specific biochemical disturbance, which in turn causes disease. Alkaptonuria is on the same metabolic pathway as is PKU and tyrosinemia. Alkaptonuria specifically is a defect in homogentic 1,2 dioxygenase, which causes a metabolic block in the conversion of homogentic acid to mallyl acetoacetic acid. And this causes an accumulation of homogentic acid, and homogentic acid spills over into the urine, causing the characteristic brown discoloration that no doubt Sir Archibald noticed. But that's not actually what causes the clinical problem. The clinical problem is homogentic acid accumulating in cartilage and also on heart valves. And in cartilage, it causes a very severe osteoarthritis. What are inherited metabolic disorders? IMDs, or inherited metabolic disorders, are caused by impaired function of a biochemical pathway for metabolism or transport of one of the major dietary fuels of protein, carbohydrate, or fats. The defect may be a genetic mutation directly affecting the activity of an enzyme, or it may be a mutation affecting the metabolism of an enzyme cofactor, which is most usually a vitamin or a metal ion. There are over 600 recognised IMDs, and individually they're rare, but collectively quite common, estimated to have a prevalence of about 1 in 1,000 of the population. The vast majority are autosomal recessive, but some are X-linked. This slide here shows a cartoon of a superficial overview of all the metabolic pathways of protein, carbohydrate, and lipid metabolism. In general terms, metabolic pathways are a function to generate energy as ATP, and this primarily occurs in the mitochondrion, which is depicted there in the bottom right-hand corner as a chain, which is the electron transport chain, and oxidative phosphorylation. And the three pathways converge at acetyl-CoA, which is fed into the citric acid cycle and thereon into the mitochondrion. The other major function of metabolic pathways is to remove toxic metabolites. And this, a good example of this is the removal of nitrogenous waste products of protein metabolism in the urea cycle, whereby urea is generated and nitrogenous waste is removed as urine. So a defect in the urea cycle leads to accumulation of ammonia, which is toxic to the brain. What are they? Well, as we've said, they're genetic defects, either directly or indirectly affecting activity of an enzyme involved in generation of energy or removal of waste products via one of the major metabolic pathways. So let us say, for the sake of argument, that the enzyme defect affects the conversion of substrate B to product C, here depicted as two red lines. How do they cause illness? So one way they can cause illness is by accumulation of substrate B. And a very good example of this is the lysosomal storage disorders, whereby glycosaminoglycans accumulate in lysosomes because they can't be broken down because of an enzyme defect. And that accumulation of glycosaminoglycans in lysosomes sets in motion an inflammatory pathway within that cell, ultimately leading to its apoptosis or cell death. Other examples include glycogen storage disorders, where glycogen accumulates in liver or muscle, or both, depending on the glycogen storage disorder in question. PKU, or phenylketonuria, which is a defect in the enzyme phenylalanine hydroxylase, causing accumulation of the amino acid phenylalanine, which is toxic to brain, and the accumulation of ammonia in a urea cycle disorder that we've already talked about. The second way in which an IMD may cause illness is because impaired conversion of substrate B to product C may cause an energy deficit if C is a metabolic intermediary for the generation of energy as ATP. So examples of these are the mitochondrial disorders, fatty acid oxidation disorders, in which beta oxidation is required for generation of ketones, which are a source of energy. And again, the glycogen storage disorders, whereby the conversion of glycogen to glucose as a source of energy is affected. And the third way in which IMDs cause illness may be through the accumulation of toxic metabolites because of conversion of substrate B via an alternative pathway. And an example of this is in tyrosinemia type 1, where succinylacetone and fumarate acetoacetate are generated, and these are very toxic to kidneys and liver. Inheritance patterns. As we said, the vast majority of inherited metabolic disorders are autosomal recessive. This means that both parents are carriers of a condition but are themselves unaffected. But they have a 1 in 4 chance of having an affected child and a 3 in 4 chance of having an unaffected child. And of those 3 unaffected offspring, there's a 2 in 3 chance that any unaffected child will be a carrier, and a 1 in 3 chance of an unaffected child not being a carrier. Some inherited metabolic disorders are X-linked, and notable examples of these are ornithine transcarbamylase deficiency, or OTC, which is a urea cycle disorder, Fabry disease, which is the commonest lysosomal storage disorder in adults, and Hunter's disease, which is mucopolysaccharidosis type 2. So I'm sure you all recall that in X-linked inheritance, carrier mothers have an affected X chromosome and an unaffected X chromosome. They have a 50-50 chance of passing the affected gene onto each child, and daughters will be carriers themselves, and sons, if they inherit the affected X chromosome, will themselves be affected because they've not got an unaffected X chromosome to offset the affected one, unlike in women. For affected males, they will pass on the affected X chromosome to all their daughters, but they won't pass it on to any sons, because the sons will get their X chromosome from their mothers and the Y chromosome from the fathers.